So we are here. How and under which assumption can we express a general function f as a Fourier sine series? So to be able to answer this question, we need to work a little bit with some features of functions, such these periodic functions. So let's see the definition. A function f is called t-periodic, where t is a positive number, if we have this identity. So f at x is equal to f at x plus t for every x in R. And this number t is called the period of f. Okay, so if f is non-constant, we define the fundamental period of f as the smallest positive number t, such that f is t-periodic. Okay, we'll see an example soon. Soon means now. Okay, so we have this function sine of x, and we know that this function is 2 periodic, but it's also 2 pi periodic, 4 pi periodic, 6 pi periodic, and so on and so on. So once we find a period, we can also have multiples of this period that make the function also periodic, but we are going to choose the smallest one, so we know that the function sine is 2 pi periodic. And how about this other example, cosine of x over 4. So we know about cosine. Cosine is pretty similar to sine, and is a 2 pi periodic function. So this function f is slightly modification of cosine. So knowing the period of the function cosine, which is 2 pi, we are going to find the period of this function x, which is cosine of x over 4. And how can we do that? Okay, so we know this. Cosine of y is equal to cosine of y plus 2 pi, because cosine is a 2 pi periodic function. So now we choose y equal to x over 4, because that's the definition of f. And we just put x over 4 where we have y. And here we just made the computation inside to get x plus 8 pi over 4. And this is exactly f of this guy, x plus 8 pi. So if we look at the corners of this chain of identities, we have that f of x is equal to f of x plus 8 pi. And this is exactly the definition of f is 8 pi periodic. So this is a period for our function f. Okay, so we have this conclusion that this function f, which is cosine of x over 4, is 8 pi periodic. And we have some general property that if we know a function that is t-periodic, then this modification of the function f of x over a is a t-periodic. So in this example, our t was 2 pi and our a was 4. So 2 pi times 4 was this, it is this 8 pi here. So you can use this general rule if you remember it, or you can use each time you find this modification of cosine or sine, you just do this by hand computation, let's say, and you can get this the period of the new function. Okay. Third example. How about these two? We have the first example plus the second example. Okay, so it seems harder than before, but we are going to say, okay, we know that sine of x is a 2 periodic function, 2 pi periodic function, 4 pi, 6 pi, 8 pi, and so on and so on. And from before, we know that cosine x over 4 is 8 pi periodic, but it's also 16 pi periodic, and so on and so on. So then we find that they share this information, 8 pi periodic, 8 pi periodic. So our function of this linear combination of these previous two examples turns to be 8 pi periodic, okay? As we say here. So fourth example, we have this function given with this graph, okay? Just a line between this point and this point, but here we are not including this point in the graph. And okay, the distance between these two guys is 2, and then this graph repeats itself all over the real line. Okay. Periodic functions in general, if we know the function in an interval of length, the period, then we know the function in the rest of the line, because it just repeats itself many times. Okay, so that's nice about periodic functions. Okay, we can compute this line, which is this x minus x plus 1, where x belongs to this interval 0, 2. And here we have this because we're including this point, and we have these brackets here because we are not including this point. Sorry, parentheses here and brackets in the other one. Okay, so this function is a 2 periodic function, as we can see here from the graph. Okay, so now we have these 4 examples about periodic functions, and this conclusion that, okay, we only need to specify a t-periodic function on the interval 0t, since then it simply repeats itself outside the interval. And as you see in this last example, this can give rise to discontinuities of the function f when the f at 0 is not equal to f at t. So here in our example, the function jumps each time a new piece of graph starts. The function is jumping, and that will mean that we have a discontinuity at this point. So in each of these points, we have discontinuities of f. Okay. We are not going to work a lot on these discontinuities, but we need to talk a little bit about these discontinuities of functions, periodic functions. Okay, here is just in our last example, we have this 2 periodic function, but with this, let's say, problem where these two values don't coincide. F at 0 is 1 and f at 2 is minus 1. And that will be just a small problem, let's say. Okay, so piecewise continuous functions and piecewise smooth functions. So this part is important for you to get the idea of what a piecewise continuous function is and a piecewise smooth function is, but we are not going to really work on this smoothness and continuity. Maybe more, we are going to work more in continuity, but not that much with the smoothness. It's just something you can have an idea, but don't worry about this too much. Okay, so we have a number C, and we denote the left and right limits with this notation. F C minus would be the limit of f at x, where x approaches C from below, and fc plus will be the limit of fx where x approaches C from above. So we have the left and the right limits. If here is the point C, these values of x are approaching it from below, and these values of x are approaching it from above. Okay, so a function f is continuous at C if we have that this limit is equal to f at C. This in particular means that these two limits that we just defined it here, the left and the right limits coincide, and also coincide with this value, f of C, which is written here. Okay. And a function f is piecewise continuous on the interval AB if this left and right limit exist, and the left and right limits are different at only a finite number of points in the rest of the interval. Okay, so let's try to see this in our example that we have here. So we have this 0, the point 0 is there, right? So if we approach 0 from below, what we get is that f0 minus, so the left limit, is minus 1. If we approach 0 from above, the right limit, so f0 plus, is 1. So these guys are different, so the limit of f of x with x going to 0 does not exist, because from one side we have minus 1 and from the other side we have 1. Okay, but that's not a problem, because this guy do exist, and the function in the rest of the interval, like here, is continuous. It's just a line. So this function, no matter that it has all these discontinuities, all these jumps, this function is a piecewise continuous function. Okay, so this won't be so bad for us. Well, here we have the list of discontinuities, and -6, -4, -2, 0, 2, 4, 6, and so on and so on. Okay, as we said, this is a piecewise continuous function on this interval 0, 2. Sorry, we were looking here maybe at yeah, so let's look at this interval because it has the length of the period. Remember that this function was a two-periodic function, so this limit exists and the limit, the left limit of x of two, of the, let's say this, let me write it down. So f2 minus also exists, which coincides with the value of, with this minus 1 here. So what we have is that, okay, this right limit exists, this right limit exists, and this left limit exists, and the function is continuous in this open interval because it's just a line. So we just proved that this function f is a piecewise continuous function on this interval 0, 2. Okay, if we take this other function, sine of x, we know that this is a 2 pi periodic function, but here we are super lucky because this right limit and this left limit coincide. They are both 0, equal to 0. So this is a continuous function. Okay, so in general, if f is a continuous t-periodic function, then we have this identity. Now, the concept of smoothness. A function f is smooth if both f and f prime, the first derivative of f, are continuous. A function f is piecewise smooth, you can already deduce that, if both f and f prime, the first derivative of f, are piecewise continuous. Okay, so here we have an example. This function sine of x is smooth because f is this function which is continuous and f prime is cosine, which is also continuous. The two periodic functions describe so this is another example, the function of our example number 4, when we saw periodic functions. This line with discontinuities, no matter that this function was has all of these discontinuities, this function was anyway piecewise continuous, and it's also we can also prove that this piece was piecewise smooth. And for the interested students, here there is a proof, but we are not going to focus on that because then in the exercises you won't have to do that. But okay, for completeness, here you have a proof of this function is piecewise smooth on this interval, but we are not going to read this now, because you are not going to, you won't have to prove this in exercises or exams or so on. But yeah, for those who want to read this proof, you can just read it. And okay, so we are ready to go to the last part of the lecture, because we already have this concept of periodic functions and continuity and these points where the function is discontinuous. And okay, so we are done with this second part. We'll see in the last part